Hello, my name is Dorothy Harris, and this is my ECE 591 Literature Review. Today, we will be looking into transformers and the Informer model, which is a transformer model for time series data over long sequences. To start, we need to understand what a transformer is. A transformer is a sequence-to-sequence model. It contains an encoder and a decoder. However, it is not an RNN. The transformer structure relies solely on using attention, self-attention, and dense layers. It does not need any recurrent connections or convolution. They process the whole input at once instead of part by part. Transformers work best with sequential data due to their encoder and decoder structure. The first key concept in transformers is attention. Attention has three major components: key, value, and query. The key and value are both based off of the encoder's input, while the query is based off of the decoder's input. Each one is multiplied by a weight, which is randomly initialized and then learned from the training data. In attention, to compute the weights, a softmax is taken of all the key values and the corresponding query value to result in its weight. Then the context value is computed by concatenating the corresponding weight with all the V values. This is done to all 1 to m values. Here is the final picture of attention. As you can see, the output of the attention layer is the context vector, which is calculated with V times the softmax of K transpose Q. Self-attention works very similarly to attention, except keys, values, and query come from the input of the encoder. Similar to the attention layer, the corresponding query value and all the key values concatenate to result in the weights. Then, the weight value and all of the V values concatenate to create the context value. This is done to all the 1 to m values to result in the context vector, which is the result of the self-attention. From here, we can look at how these parts are put together to create the transformer model. To start, regular self-attention, which is referred to here as single head self-attention, can be combined with other self-attention layers to create multi-head self-attention. This process also works for attention, and both are used in the transformer model. Here is a look at what a transformer's encoder block looks like. It has 6 blocks, with each block being a self-attention layer and then a dense layer. Here is a more in-depth look at what the encoder block looks like. The input is taken into a multi-head self-attention layer, where the output of this is then run through a dense layer. This result is then the input of the next block, which is another multi-head self-attention layer and dense layer. Here is the transformer's decoder block. This block takes its own input as well as the output from the encoder. Its input goes through a self-attention layer, and then both that result and the output of the encoder are inputs to the attention layer. Then it goes through a dense layer. This can also be seen in detail here. As you can see, both the attention layer and the self-attention layer are multi-head attention. All of this put together results in the transformer model. One application of the transformer model is for predicting time series data. The Informer is a transformer model attempting to do long sequence time series forecasting. One of the problems this model is trying to solve is that LSTF requires high prediction capacity to capture long-range dependencies, which most other models are unable to provide. Another problem is with transformers. They require quadratic time complexity, high memory usage, and the encoder-decoder architecture, which are all limitations. This paper included 4 contributions to be able to combat these issues. To start, the Informer model is able to enhance the prediction capacity in long sequence time series forecasting. It is able to capture individual long-range dependencies between outputs and inputs. Next, they propose a new type of self-attention that they call ProbSparse self-attention. It was created specifically for improving time complexity and memory usage in the self-attention layer. Then, they add a distilling after the self-attention layer. This was added to reduce the total space complexity, which helps with receiving long sequence inputs. Lastly, they proposed a generative style decoder. This has only one forward step in order to acquire a long sequence input, which avoids cumulative error during the inference phase. Here is the overall block diagram of the Informer model. On the left, the encoder receives a long input sequence that goes through the encoder structure. As you can see, it uses the pre-stated ProbSparse self-attention instead of canonical self-attention. The blue blocks between the self-attention blocks are the self-attention distilling blocks. This results in a concatenated feature map, which can then be used in the decoder structure. On the right is the decoder. It receives a chunk of the input as well, but it pads part of it with zeros. This part is padded with zeros because it is where the predicted output will be after going through the decoder block. This then goes through the decoder structure, which uses the newly proposed ProbSparse self-attention and regular attention with the encoder's output. This results in it's put through an FC layer to then return the generated output. Here is an example to better understand the size. If the input is of size 96 by 7 after going through the encoder, it will result in half of the original size at 48 by 7. The input to the decoder is the same size as the encoder's output. However, it is the last 48 by 7 of the input sequence, as well as 24 by 7 zero padded values for where the result goes. This result is 1/4 of the original input's size. ProbSparse self-attention was created specifically for proving time complexity and memory usage in the self-attention layer. Regular self-attention uses the equation A of Q, K, and V equals the softmax of Q times K transpose over the square root of D, all multiplied by V, as seen prior. From this, however, multiplying the Q matrix by the K transpose matrix results in an LQ by LK matrix, which is a lot of memory usage and a drawback to enhancing prediction capacity. The theory behind ProbSparse self-attention is that looking at the queries by keys features map, the value of the rows can be related to a uniform distribution. Some of the rows have a lot of variance of their values in the row, whereas others are relatively the same, becoming almost the uniform distribution itself. They call these rows that have a lot of varying values active, and the ones that do not have as much variance lazy. There is a lot to learn from these active queries, and not so much at all from these lazy ones. So, therefore, we want to focus on the active ones, and the lazy ones can be assumed to be the uniform distribution. To do this, ProbSparse self-attention tries to minimize that number by making it L log L instead of L squared. It uses the same equation as regular self-attention, except with an altered Q. Here is pseudocode explaining how ProbSparse self-attention works. It takes in a Q, K, and V like regular self-attention. Then hyperparameters are set with C just being a constant sampling factor. Little u is C times ln of m, which is the length from the query. Big U is m times ln of n. which is the length of the key and value. Then, dot product pairs are randomly selected for k. The random amount is the value calculated for big U. This gives a smaller random sample of k in order to use it for calculating the next part. But because it was random, it is determined to be a relatively accurate estimation of what k looks like. Then, we can multiply q by the new k transpose. From this result, we want to see only the greatest difference values. So we take the max of this result and subtract the mean of all the values. Then, only the largest ones are chosen from this, and the amount of them chosen is the value of little u. From here, we can go back and do the regular self-attention equation with the now adjusted value for q with the original value for k to get S1. S0 is where the result goes. These two parts are concatenated together to finish off the ProbSparse self-attention. Because of ProbSparse self-attention, there are redundant combinations with the value of v. Distilling is used to trim the input's time dimension, and does this by giving superior values dominating features. This makes a focused self-attention feature map. As you can see, it takes the attention block and does a 1D convolution with ELU activation. Then, a max pool is done to grab only the superior features, which uses a stride of 2 to half the input, or half the amount. Here is a block diagram of the encoder block, as well as the components to the block in detail. Here, I have circled the parts of the model that correspond to the details and the original block diagram. As you can see, it takes the input string and concatenates it with a 1D convolution. This is the input to the ProbSparse self-attention block. The output of the self-attention block then goes into the distilling, which is the 1D convolution, and then the max pool, which halves the length. Then this is done again to reduce the length for a result of 1/4 of the original. The decoder structure takes in the input and does ProbSparse self-attention with a mask on the part that will eventually be the output. Then it does regular attention with the output of the encoder and a FC layer to return the output. Here is an example of how the decoder works. If we want to predict 168 points, which equals 24 points a day for a total of 7 days, then we take the last 5 days before as the start of the sequence. To the decoder, we feed in an input of the values for the past 5 days, as well as the 0 masked values after, for the result to go in. Then, the decoder predicts the output with only one forward procedure. Here is a quick overview of the results found from this paper. As you can see, when looking at univariate long sequence time series forecasting over multiple different datasets, the Informer model tends to work the best. They also tested how well the Informer model works with regular self-attention instead of the proposed ProbSparse self-attention to show that it did, in fact, make the model better. Here are the results of how well the Informer model does with multivariate long sequence time series forecasting. Like before, the Informer model tends to do better than other models, and the Informer model is tested without ProbSparse attention. On top of making sure ProbSparse self-attention contributed to improving the model, it was also checked if the distilling and the decoder structure contributed to the model's success. This was done by testing the model with those components removed or replaced with the canonical method. It can be seen that all of their contributions aided in making the model successful. Here are the references to the papers, as well as some helpful resources on the concepts. Thank you for listening to my presentation.